So if you're there to hear my introduction, you know that macros are close to my heart. They're what brought me to Clojure, and they also helped me land my first what's this one? Tech Talk. Tech Talk. Yeah. So macros look very similar to functions, and especially trivial macros look similar to functions, but they behave differently from functions. And there are two main differences with functions. The first one is the arguments passed to the macro are not evaluated. So you've seen a function and there's a print inside the body. So when we pass a print here, it's evaluated first before being passed to the function. So that's why you get hey inside the body and nil. But if you look at a macro, it's the same macro, it looks exactly like the function, but it behaves differently. So here, when you're calling the macro with println, it first prints inside the body and then hey, which is different from the function call. It's sort of switched. That's the first main difference. The second one is the data returned by the macro is evaluated afterwards. So let's look at this function. This returns a list. When you call foo, it returns a list of 1, 2, 3. Now, if we do this, where we're evaluating foo twice, it returns an error. Now, this will become, you'll understand why I've done this in a bit. So when you call a macro, we define a macro foo with list 1, 2, 3. It looks exactly like the function, but when we call it, it returns a class cast error. So you can, when you relate it to this, when you're evaluating it twice, you get the same error. So that sort of gives you an idea that data is being evaluated twice in a macro. So macros return some data and that gets evaluated. And if you want to see what the macro is returning, you can use a tool called Macro-expand. And when you macro-expand foo, you get this list. So there is a sort of double evaluation that's taking place. And this is the source of power and confusion also for macros a lot of times. But this double evaluation is important and we'll get back to it in a bit. Let's take a step back and actually think about what we do as Lisp programmers. And you might say that we build programs, and that would be right, but not fully accurate. The reality is we build lists. We write lists and we put data in lists, and those lists happen to be data that can be evaluated. And for example, if you look at this, you might think that the first one is a function call and the second one is a list. But actually, both of them are lists. They're 3-element lists. And because they're lists, you can have list operations on them. You can count the elements, you can swap them around, you can add elements, you can conj elements to the list. And this is powerful because we can manipulate lists now. So in Lisp, we create lists. That brings us to the question of what is a macro? And a Lisp macro is a Lisp programmer, actually. So how did we get a Lisp programmer? And there is a story to this, and the story goes this way. Back in the day when Lisp was young and beautiful and didn't have square brackets, there was a programmer named Marco. And Marco was a wizard with computers. He could do things with Lisp that no other programmer could do. And then, and Lisp fell in love with him because of that, because of his brilliance. So then Algol 60 came, and Algol 60 was the hot new language on the block with a syntax that just won't quit. And Lisp got insecure. Lisp thought Marco would leave her for Algol 60. So she asked Marco if he would marry her. And now Marco, who wanted to know Lisp at a deeper level, said yes. And they were married by Lisp's father, John McCarthy, in the Temple of Parentheticus. That's where we get a parentheses from. And there was one photo of the wedding, which I will show in the end. But after the honeymoon phase and the marriage, Marco got bored because he missed programming. He was stuck inside a compiler. So he told Lisp this, and Lisp went to her father, and John thought of something, and he said, well, maybe I can I can let you talk with other programmers, and you can help them write programs. So he made that happen, and now this was a selfish thing because John was afraid that Algol 60 might take over. So that's why he let Marco communicate with other programmers and access the compiler. And while he was making sure that happened, he misspelled his name, and it was misspelled from Marco to Macro. And Marco was not very happy about that, but we'll get back to that later on. Anyway, it's a small story, but yeah, the analogy is useful of treating a macro as another programmer. And we'll get back to that in a while. So the next important thing we need to talk about is symbols and values. This is quite confusing for me. This was quite confusing for me and for most people. That is because we are used to resolving symbols to the values. Our brain does it instantaneously. Here's an example. What comes to your mind when you see this? If you're like me, you probably thought about this, a dining table. And if you're really nerdy, you thought about this. So the thing is, none of us stopped for a moment and thought about the word table. Like, what is it? We never thought about the symbol table. And so that's why it's quite hard to talk about symbols. Let's see what happens when a brain does not resolve the symbol. What do you think is this? Now something different happens. You start looking at the symbol and you start wondering whether that's a banana peel, or is it a person trying to do a split, or is it a lambda with arms? But the important thing is we're thinking about the symbol now. We're not thinking about its value. And to the smart people in the audience that think this means table, it means a dog. So this is, we have done this quite often. We're assigning the symbol 1, the value of 7. And when we call the symbol, it resolves the value. And we are so used to doing this, the process of resolving symbols to values, that when we write functions and things, we mentally substitute the symbol for its value. And Clojure gives us an easy way to refer to symbols. We do that with the quote. Now, this is a simple quote, and this is the backtick. So the quote can let us refer to symbols. So here we're not resolving the value of 1. And the backtick, or the syntax quote, lets us refer to namespace symbols. Now, we can evaluate symbols, and symbols evaluate to the values. This is something we have seen before, nothing new, nothing special. But the real mind-bending thing is that symbols can be assigned other symbols. This is where it gets confusing, because the symbol 2 we can assign the symbol 1. So when we call 2, it is also the symbol 1, not the value of 1. And when we evaluate it, this is a double evaluation. It returns the symbol 7. So this makes us ask, are symbols values? And yes, they are values. But for the sake of this, let's treat them as separate things, because it gets confusing later. I like to think of symbols in two different categories, like predefined symbols and user-defined symbols. So these are predefined symbols. Right? Here, what happens is this is a symbol, 420. But we are so used to resolving it to a value, we can't see the symbol, we just see the value, 420. And since this is so commonly used, like integers, vectors, and strings, the compiler already knows how to resolve these two values. So that's why I say these are predefined values. And now this is a function where nums is a symbol, but we don't know the value of nums. And since we don't know the value of nums, the compiler can't know the value of nums. So this is something that is defined at runtime. The value of this symbol is available at runtime. So let's revisit double evaluation. Now I said that with the whole story, I said we have access to a Lisp programmer. Now we can think of writing a macro as writing instructions for another programmer, for Marco. And so when we write instructions for Marco, Marco needs to read them at some point and come and write the programs. So this happens when we are compiling things. So once we are done writing the instructions, we send it to the compiler. Marco comes, reads the instructions, and then he writes his program. And that program, the one he writes, is evaluated at runtime. So that's why we sort of have two evaluations, because the first time to read the instructions, that's one evaluation, and at compile time, at runtime, sorry. So when we write, what I mean by write time is when we're defining functions, everything is a symbol. There are no values to them. And when we compile them, some of the predefined symbols can be resolved to values, but user-defined symbols can't be. And at runtime, all the symbols are resolved to values. In a correct Lisp program, of course, because if it's not correct, then you might get an unresolved var exception. So I bring this back because when we are writing this function, we know for sure that nums is going to be resolved to a value. So mentally, when we're writing this, we substitute the symbol for a value and we operate on it as if it were a value. So, and this doesn't happen in macros. So in functions, we manipulate values. But in macros, as I said, at compile time, only the predefined symbols are resolved to a value, but the user-defined ones are not. So Marco has to juggle values and symbols. So in macros, we manipulate symbols and values. That's why it gets confusing. Let's write a macro, finally. We're all familiar with this, hopefully. And what about this? Do you think this is valid Lisp code? how about this? And this is valid Lisp code, right? This is a vector of 3 elements. And the way this is also a list. So both of them are valid Lisp code. It's just that this can't be evaluated. It's not something we can evaluate, but it's still data. It's still a list with 3 elements. But we can, change it up a little bit to make it something Lisp can evaluate, like this. It's still a list with 3 elements, but now this is something Lisp can evaluate. This is the transformation we're doing. We're swapping elements. Now let's generalize this. So LT is left operator and right. And we're swapping the first 2 elements of the list. So once we know what transformation we're doing, we can write the macro. So we write macros with def macro, it's infix, and some destructuring going on here. And we are swapping the elements here. Now, we have seen the syntax code before. So if it comes before a list, it recursively quotes each element in the list. And then you see these squiggly lines here. That's a way to tell Marco that, hey, this symbol, resolve it to a value. Because we don't want the symbols OP, LT, and RT. We want what they refer to. So if we call it with data, we get it works. So we're taking data, which is not valid Lisp, which is not a valid Lisp expression, and we're converting it into a Lisp expression, and that is evaluated again. So this is a very trivial macro, but we went through a 3-step process in it. And if you've never written a macro before, this is a good guideline. This is what I use to help me write macros. So the first step is think about the data the macro will get. So in our case, it was a 3-element list. And then you can think about the data the macro will return, which is a plus. This is what it returns. So you're swapping the elements. Then we have to think about how we transform that data. How we're going to make the transformation happen. This is where we do the heavy lifting of writing a macro. So that's it for the 3-step process. Let's write one more macro. I want to show something else. And this macro is called print elements, where we print each element on a separate line, and then we return the data of the element. So as you can see, this is how I expect the output to look. One way we can do it is we map print to each element in the vector, and then we return the vector itself. So this is a rudimentary implementation of the macro. It seems pretty straightforward. We're doing this, but it doesn't work. And here's why. You get a can't call nil from this. Let's macro expand to see what the macro is actually returning. And here, these are the side effects that are print. That's not important, but let's look at the form. You get a nil, nil, nil. It's a list of 3 elements with nil. So what Lisp does is, because it tries to evaluate the first element as a function, it tries to call it as a function, and nil is not a function, there's an error. As you can see, it says can't call nil. So what we really want to do is something like this. We want this to come out. We don't want this to be in a vector, inside a list. So there is an operator for this, and it's called the unquote-splice. So think of it as a sledgehammer that Marco uses to break down a list and empty its contents into the parent list. So if you try to macro expand this, you get what we expect. Now, remember I mentioned that Marco was not happy about John McCarthy misspelling his name. So he's kind of naughty sometimes and trouble. He likes to trouble the programmers when he can. And one of the things he does is symbol capturing. Let me show you what I mean by this. So we have a macro, returns some list, and it returns a let binding, where 1 is bound to the symbol, the integer 1, and returns a vector with x. And just seeing the usage, we get what we expect. But what happens when we define 1, the symbol 1, to a string 1, and we call it list? We see two integers 1. It's not something you'd expect. And let's macro expand to see what's happening inside. So you see you're returning a let. And here 1 inside, so let creates its own lexical scope. So here when we assign 1, the integer 1, the symbol 1, the integer 1, and Lisp doesn't know, Lisp resolves these to this one. So that's what happens. This is when Lisp is capturing the symbol, because when we pass the symbol, we are passing the symbol 1 here, and this symbol is captured, and instead the one defined in the local binding is returned. So how do we prevent this from happening? And there's a tool for this. It's called the auto gensym. And this guarantees that the symbol generated is unique. This is a promise Clojure gives. But the interesting thing to note is there's a syntax code here. You can't use it without the syntax code. So the first thing, so if you want to rewrite our macros, the first step is to use the syntax code instead of a simple code. And it will look something like this. And now adding the auto gensym. This is our final macro. To make sure it works, we call 1. And now it's resolving to the symbol, the string 1. So common macro gotchas. And these are mistakes that I still make, and I've made a lot of times. The first one is not resolving arguments to a value inside the macro. So revisiting the infix macro, you see these things, and we are returning the symbols the way they are. And if you macro expand them, we get, so we are passing, even though we are passing 1 plus 2, we get OP, LT, and RT. And this is not something we want. In fact, I made this exact same mistake in the presentation earlier, and I realized it later on. But this is a common mistake, and it happens. So if you're using symbols from the arguments, like you're using these arguments, make sure you resolve them if you're quoting them. The second one is when the macro is not the first element in the list. If you see something like this, then you're definitely doing something wrong. The macro always has to be the first element in the list. And why we can't do this is something we'll revisit later on. Third one is passing a symbol instead of a value. And let's see this macro. So here, when we define the macro, x's, we are unquote-splicing. So that means we are expecting x's to be a collection, a value, a vector. And it works fine when you're passing it a vector. But if you are using it in a function, like multiply by 2 in nums, and you're passing nums to it, you'll get an error. Because nums at compile time is a symbol, and it's not a value. So that's why you get this error that can't create IC from closure line symbol. And I have made this mistake a lot of times. So this happens because when we are defining the macro, we sort of assume what we are going to get. And sometimes we have to make sure that we are assuming the right things. So whenever you're writing the macro, always think whether you're going to get a symbol or you're going to get a value when you're calling the macro, and define it accordingly. So some practical advice: always use a syntax quote, because the syntax quote has a lot of guardrails built by Clojure developers, and it will help save you from common macro pitfalls. This is very famous advice in the community, and I personally don't like this so much, because the whole reason I learned to Lisp was because macros are so powerful. And after I learn it, and I come to know that I should not use them. So I'm just going to leave this slide here, and I'm going to say actions have consequences. So what are the consequences? So the first one is macros are infectious. So before Marco, the programmer, married Lisp, he worked for a company, and his boss really liked him a lot because he could ship code really fast and features really fast. So when his boss would tell him to ship a feature, he would finish it in an hour and he would ship it. So then management came along, said we need to change some things. So when the boss saw the code, he realized that, oh God, this is not readable. So he sent it back. He told Marco, hey, come here, just change this and ship it. Marco, being Marco, he said, sure, why not? And he shipped it. He added more code. And slowly, what happened was the whole code base was written by Marco, because only Marco could change his code and no other programmer could, because it was so unreadable. And while this analogy is not, it's not a reason why macros are infectious, but hopefully it gives you a good picture about what happens. Here's an example of what I mean by macros are infectious. And so this is an add macro. It takes args and it returns this. So when you call this 1, 2, 3, it works. Now suppose we wanted to do something else with this add, something like this, where we have a vector and we wanted to find the sum of the elements of each vector and get a value like this. This is quite trivial when we use the function add. But if we had to do it with a macro, it would not be possible. We would get an error. You'd get an error like can't take value of a macro. So if you wanted to make this possible with a macro, you'd have to do this. This is quite a big macro, and I'm not going to explain it, mostly because I don't remember what it does. I'd written this a long time ago. But the bottom line is it works. You can add and do it. But you've seen how we started with something so small, one simple macro, and if you wanted to extend it, we had to write another one. In this way, now if you want to extend this and use it for some other things, you would have to write another macro for that. So in this way, macros become infectious. They can quickly infect a whole code base. So what we learned is macros are not reusable. We could not reuse our add macro. If macros are not reusable, macros are not composable. And we all know that composition is king. Even the O folks know that. So what is so functions and data are more composable, and that's why the Clojure community recommends not to write a macro. So when should you write a macro? And then there's a simple answer to this: when a function just won't do. But you must really ask yourself, like, is this something a function can do? Have you really tried uh, doing it with a function? And if not, then you have to use a macro. So one very important indicator that you need a macro is when you need to prevent the evaluation of arguments. An excellent example of this is in Cantor's infix macro. So we've seen we've written infix macros, and this is actually quite a big macro, and you should read it whenever you get time. So the next thing is when you want to extend another macro. So as we saw with our add macro, we wanted to extend that macro, and we had to write another macro for that. Then syntactic sugar. So my favorite example of this is the threading macro, because the threading macros, they're not essential as such. We can get work done without them, but they make things so easy for us. And it looks so pleasing and beautiful to write them, use them, that it's well worth creating some syntactic sugar. And there's a subtle benefit to it, is that we are forced to write code in a way that it's a transformation of data, because it's so pleasing when you can fit a computation in that way. And the last one is speed, not that kind. And if you can use macros to speed up some code. And for this, I will show an example. So this is okay. Is this legible? Can people see this? Do I need to zoom in more? Yeah. All right. So this is my library, Luna. It's a regular expression DSL. So right now, everything is a function. So we are going to benchmark this. I'm using criterion for benchmarking. Yeah. And let's benchmark this right now. Okay, so about this much. Now let's change this pre-function to be a macro. And this is so trivial. When I first did it, I really couldn't believe myself. That's it. Now this is a macro. And we can benchmark this. So yeah, all right. So the benchmarking is done. So with the function, it was, sorry about this. Yeah, it was a couple of microseconds, like 200 microseconds. And when you convert it into macro, it's nanoseconds, 6 nanoseconds. And for reference, 1 nanosecond is 1,000th of a microsecond. So that's roughly, I think, 40,000 times faster. Don't quote me on that. What's interesting about this is that this is a language I defined. And when I made this a macro, This got compiled. That's why it's so much faster. This was compiled by Lisp. So I just taught Lisp how to compile my language. And if you think about it, that's kind of cool. And this is what they mean when they say you can extend the language itself, because now Lisp knows a whole different language on how to compile. So yeah, that's it. Now, I did promise, okay, I did promise a wedding photo of Marco and Lisp, and this is it. All right, thank you.